existence and removable sets. This talk is based on joint work with Igor Babitsky, Tadala Mangesha, Quoc-Hung Nguyen, Kathik Adimurthy, and Ken Oy. All right, so let me start with some facts on harmonic functions. So in the first course in PD or in complex analysis, we learn about the so-called Weiss lemma. It said that if a function, if U is a distribution solution to the Laplace equation in the domain omega, then U is smooth, and quantitatively you can control any order of the derivative of U in L infinity norm by the L1 norm of U or by the oscillation of U in a little bit larger ball. And this marks basically the beginning of the regularity here. And the second thing that we learn is about removability of isolated singularities. If U is a harmonic function in omega minus a point x0 inside that domain, then U can be extended to a harmonic function in the domain omega, provided that U doesn't blow faster than, doesn't blow up faster than the fundamental solution. Okay, so the gamma x here is the fundamental solution for the Laplace equation, and this implies, in particular, that the non-existence of a continuous function U such that Laplace of U is 0 in the unit ball minus the origin, U equal to 0 on the boundary of the unit ball, and U equal to 1 at the origin. And of course, this is relevant to the so-called Wiener's criterion of irregular boundary points. And now let me talk about removable non-isolated singularities. It said that if U is a harmonic function in omega minus E, where E is a compact set in the domain omega, then U extends to a harmonic function in omega, provided the two capacity of E is 0, and U is bounded in omega. And because the two capacity, if the two capacity of E is 0, then the L infinity, the Lebesgue measure of E is 0, so the L infinity norm of omega is the same as the L infinity norm of omega minus E. And by saying the two capacity, I mean that the capacity associated to the homogeneous superlap space W12 dot IN. So I don't restrict to any domain here, I just work with IN. Okay, so you minimize the definition of the two capacity, that you just minimize the L2 norm of the derivative, and you square that over all function phi, smooth function, and phi is bigger than 1 on a set K that you want to calculate the capacity. Okay, this removability condition, the capacity condition here is sharp in the sense that it is also necessary in the class of bounded harmonic functions. Okay, so because of that, we cannot, for example, replace the two capacity by 2 minus epsilon capacity for any small epsilon. All right, and here when I say P capacity, I mean the definition is similar. You just replace the 2 by the P here. And the other sufficient condition are also available. For example, you can replace the capacity condition by the finite Hn minus 1 Hausdorff measure condition, or you can replace it by 0 Hausdorff content. But those conditions are not sharp. Okay. Now, and you can see that if you look at this infinity condition here and this decay condition, they don't match, right? And the reason is that This is just one point, and this is the condition for basically for very large set. So if you make the set, if you assume that your set is smaller, then you can replace. I mean, you can weaken this infinity condition, and the result is this: if the set E is smaller, then we may require the weaker condition on U, and the statement is like this. Suppose that the capacity, I mean the S capacity of E is 0, where S is between 2 and N. If U is harmonic outside E, then U extends to a harmonic function in the whole domain omega, provided that for some epsilon, U is in this Lebesgue space, S times 1 plus 0 divided by S minus 2. Of course, when S equal to 2, you get the condition that U belong to infinity of omega. Now, you also have similar result for superharmonic functions. Okay, if U is superharmonic outside E, then you extend to a superharmonic in the whole domain omega, provided that the two capacity is 0. But here you need the condition that U is non-negative, but you don't need any boundedness property of U. Okay, and the extension can be given explicitly. You just take the essential lim inf of U at any point x in the domain, and that gives you the exact extension, right? So now, so that was the classical theory and linear theory, you would say. Now let me tell you a little bit on the nonlinear theory. So the nonlinearity appear in the talk lie in both in the principal operators and in low order terms, right? The main principal operators, the first one is the B Laplacian. And well, we see this several times already, okay? So we just define the divergence of this vector field. In most cases, it can be replaced by a more general quasi-linear operator, L sub PU, which is in the divergent form like this, and the nonlinearity A here is assumed to satisfy certain rho and monotonicity conditions. Okay, so this is standard. You see this in a talk of Rossio and Bayun, and sometimes we need stronger monotonicity condition and regularity condition as well. So those are the condition, and we also need certain smallness. I mean, maybe some continuity assumption on the in the x variable for the function A, right? But I'll tell you more detail later on. And another nonlinear operator that I want to mention is the so-called K-Hessian operator, defined for k integer k from 1 to n. F sub k of U, okay, F sub k of U, is defined as the sum of k times k principal minor of the Hessian matrix of U. Okay, and that means that you can write down the sum as the sum of the products of those eigenvalues of the Hessian matrix. In particular, F1 of U is the sum of the eigenvalues, so you get the Laplacian, and Fn of U is the product of the eigenvalues, so you get the so-called Monge-Jambert operator. Well, another way to think of f sub k of U is the following: you look at the Hessian matrix, and then you calculate, you try to compute the characteristic polynomial for that Hessian matrix. And the K Hessian of minus U here is exactly the coefficient of lambda to the power n minus k. All right, so this is essentially just a coefficient when you expand your characteristic polynomial. I mean, when you calculate the characteristic polynomial. And so I define here when k equals 0, I define f sub 0 is just 1. Okay? All right. So the point I want to make is that the underlying capacity for the B Laplacian is exactly the B capacity. And this is the classical, by now it becomes a very old result of Serine, which say that if U is the harmonic in omega minus E for combustion E, then you extend to a B harmonic function in the whole domain omega, provided that the P capacity of U is 0 and U is bounded, all right? Up to the domain, up to the set E. And you also have a similar result for a non-negative B superharmonic function. You can always extend it provided that your function is non-negative and your set has 0, sorry, this should be B capacity, okay? And the extension is just the essential lim in. All right. And now the underlying capacity for a K Hessian is the so-called K Hessian capacity. Well, the definition is a little bit complicated. So you look at this sub over this integral of x of k of v, okay, where the sub is taken over k convex function v in omega, so that minus v equals to 0 and 1. Well, this integral here should be understood as the measure of the set k. So x of k of v should be understood as a non-negative measure in omega, the so-called K Hessian measure. Okay, this is the result of Turing and Wang. It turns out that, well, of course, we are not satisfied with this definition because we want to work with Sobolev capacity, right? And it turns out that there is, at least locally, there is equivalent between this K Hessian capacity and the Sobolev capacity. And this was done in my work with Igor Verbitsky. So locally, this K Hessian capacity is equivalent to the Ritz capacity, okay, or the B fractional B capacity, you can say. So the order of derivative here is a fractional order, 2k over k plus 1, and the degree of integrability is k plus 1. So here you minimize smooth function phi, where phi bigger than the set k that you want to calculate the capacity, over the norm of phi in the inhomogeneous, homogeneous Sobolev space W, 2k over k plus 1 and k plus 1 here, and you raise to the power k plus 1. Okay, and I just want to mention that. So what is a k convex function? Well, you can just use comparison principle, or you can use viscosity to define it. But one way, I mean, for simplicity, you can just think this way: a C2 function is k convex. This is a notion of subharmonicity. A C2 function is k convex if and only if x of j of p is non-negative for j from 1 to k. So I require non-negative non-negative here for all j from 1 to k, not just at k. Okay, so it's so this is a little bit different from the notion of p harmonicity. All right, and one of the fundamental results on removable singularity is due to Labutin. So for k between 1 and n over 2, if you solve the k Hessian, I mean, if minus you solve the k Hessian equation in omega minus e, then you can be extended to the solution to the whole domain, provided that this capacity is 0. And of course, originally, Labutin did it for the k Hessian capacity, but you see, because of the equivalence, this is the same as for this capacity, and U is bounded in omega minus e. My statement here for k from 1 to n over 2, not including n over 2, but it's also true when n equal to k equal to n over 2. But then you have to use the so-called Bessel capacity, or capacity associated to the non-homogeneous Sobolev spaces. Okay, all right. Now the same also hold for non-negative U, so that minus U is k convex. So very similar to the case of B Laplace equation. All right. So what's next? Okay. So now, let me talk now. Let me mention about equation with measure data and nonlinear potential theory. So a strategy, well, to guess the underlying capacity is to consider the associated equation with non-negative measure data. Okay, so if you want to find out what is the capacity associated to the function, you can just look at this equation, or for the beta plus equation, you look at this equation with measure data, and then for the K Hessian equation, you look at this equation with measure data. Then you find the precise bound for solution in terms of potentials. This is very, in general, it's not trivial. For Laplace equation, the potential is, of course, the nonlinear potential, right? For others, potential, the tangential potential are the so-called work potentials. These are fundamental results due to Kubelainen-Marlies and Laboutin. And finally, an application of nonlinear potential theory will help you to determine the associated capacity. Well, maybe you don't have to do that much if you are working with the Laplace equation, because you can really guess the associated capacity by the fact that solutions are minimizer of the Dirichlet integral. But if you work with the Hessian equation, it's not that trivial to guess, right? All right. So now let me bring in the lower order term, right? So now we consider the semi-linear operator, minus Laplace u minus u to the q, say q bigger than 1, and I work with non-negative function locally in LQ. And the following result suggests that the nonlinear term u to the q could interact with the Laplacian and change the underlying capacity dramatically. All right. This is due to Barras-Pierre and Aram-Pierre. So let E be a compact set in the domain omega, and Q is bigger than n over n minus 2. In the condition, I mean, the capacity 2Q prime equal to of E is 0 is necessary and sufficient in order that any solution outside of set E can be extended to a solution to the whole domain E. So essentially, I mean, in other words, the removable set for this operator here is exactly the set of zero capacity, and the capacity is no longer the P capacity anymore. It's the capacity associated to the subspace of order 2, and the real integrability here is Q prime. The Q prime is the whole conjugate exponent of Q. All right. So it's no longer 1Q or 1, 2 anymore. Okay. So there's an interaction here between the capacity and Laplace and the nonlinear term. And this is sharp because it's necessary and sufficient condition. So I want to make some remarks here. Of course, the capacity 2Q prime here is larger than or equal to the capacity, the 2 capacity. And here, you know, the capacity 2S is defined, you can just define like this. You minimize over this expression. Okay, so here you bring in the second derivative, and then you deal with LS now here. And another interesting fact is that no information of U near is needed for this for the removable singular set here. What do I mean by that? Well, you look at the assumption here. You need only that U is LQ local away from E. So that means that you have no information on E. So here is a local thing, okay? So that means that it could happen that U could blow up when it go to E, but eventually it's still in LQ up to E, all right? So here, this is not a typo, okay? It's actually locally in omega minus E. All right, so it means that no information of U near E is needed for this removability problem. And I just want to mention that the proof of a necessity part. So say, if the set is a removable set for this equation, then the capacity have to be 0. The proof of that turns out that the proof of that requires the application of nonlinear potential theory and the solvability of the associated equation with measured data. Okay, so this makes my point earlier. Like, if you want to study the associated capacity, then you just still look at the equation, I mean the associated equation with measured data. And okay, it makes the point like, why do we need to study equation with measured data? Okay, at least for those problems. Okay. In my talk today and tomorrow I will discuss the corresponding results for doubly nonlinear equations. So I think today I will cover the first 2 equations, and tomorrow I will cover the second equation. So you can say that this is the full taste of nonlinearity because you have nonlinearity on the left side, and you also have nonlinearity on the right side. In the work of Barras, BR, and Aram BR, you still have nonlinearity on the left side, so you still have some advantage. And but here, you know, nonlinearity is in both sides. Okay, so it's the full taste of nonlinearity. Okay. So I want to mention one more thing before I move on. So let's consider again the equation. Okay. Minus lambda u minus u to the q equal to 0. U is non-negative in the domain omega. So I look for non-negative solution only. So let's define the so-called singular set for this equation. The set S of points x in omega for which u is not bounded in any neighborhood v of the point x equal the singular set of u. Okay, so because of that removability result, you would expect that the size of the singular set should be the set of zero capacity. And actually, this is essentially the conjecture of Parker. So he conjectured in 93 that for q larger than or equal to n over n minus 2, the house dot dimension of S is less than or equal to n minus 2q or q minus 1. Of course, the stronger conjecture would be the capacity 0. Okay, and this should be the capacity order 2, and the degree of integrability is q prime. At least for q less not equal to this, because otherwise you have to use the Bessel capacity. Okay, and well, at first I know this is still an open problem. There are sufficient conditions to get this result. You have to assume some smallness on the jump of the singularity. Okay, so if you assume some smallness at the jump of the singularity, then this is true. But the result without any condition is not known to me. Okay, so but I want to, my point is that basically, if you know the removable set, I mean, that doesn't mean that you know the singular set, okay? Because you have to prove it, and you cannot apply directly, okay? You can extend, but then you can extend it, but the extension, the solution of the extension, I mean, is still singular, okay? Because we understand this solution in a very weak sense. The solution in a very weak sense. All right, so let's move on to potential theory, okay? So this thing gonna be mine, okay? So maybe many of you here already know this. Let me just say this: the history of potential theory begins in the 17th century. Founders include some great mathematicians as Newton, Euler, Laplace, Dirichlet, Riemann, Weierstrass, Gauss, Poincaré, etc., etc. One of the important objects of potential theory is, of course, the capacity. Okay, so for us, we are interested in the so-called Sobolev capacity. Okay, so look at the Sobolev space. Say this is the homogeneous non-homogeneous Sobolev space W alpha S. The alpha here is the order of derivative. It may not be integer, and S is some number bigger than 1. So to calculate the capacity of a set of a compact set K, you minimize the norm of a function U. There is a misprint here. This should be S. There is a power S here. Okay, you minimize the norm, the Sobolev norm raised to the power S for all function U smooth and U is bigger than or equal to 1 on the set K that you want to calculate the capacity. Okay. All right. And functions in the Sobolev space W alpha S are, this is well known, generally not continuous, and one can think of this capacity as a device to measure the discontinuity of function in W alpha S, especially when alpha S less than or equal to N. Okay, and you have the so-called Louisiana theorem for function in W alpha S. So any function f in W alpha S always have a quasi-continuous representative f tilde, and so that means that f equal to F tilde almost everywhere, and F tilde is quasi-continuous in the sense that for any epsilon, there is an open set G, so that the capacity of G is less than epsilon, and F tilde is continuous outside G. I mean, the restriction of F tilde is continuous in the N minus G. Okay, these are basic things. And another capacity is, it's more convenient for us, is the so-called Bessel capacity. Okay, so you minimize the LS norm of F, where the potential of F is equal to 1 on the set K. And this definition is defined for any set, not just compact set. Previously, you define for compact set, and then you can always extend it to any set using the usual extension procedure. The G alpha here is the Bessel function. Okay, Bessel kernel is defined as the inverse Fourier transform of this function. Okay, and by G alpha F, I mean the convolution of F and the Bessel kernel, G alpha X minus 1. And of course, by Caron's theory, the superlap space is isomorphic to the Bessel potential space, the space of all F, of all G alpha F or F in MS. And because of that, the superlap capacity is equivalent to the Bessel capacity. Okay.
I think the complexity of SOLAP W emphas power S should be power S, right?
Yes, I did. I said that.
Yeah.
I said that. I just mentioned that, right? I said that there is a power S in here.
Yeah. Okay.
Yeah, it's a typo. Thanks. All right. What else can I say? Okay, let me hide it. Somehow it's all right. All right, so there's another capacity, this risk capacity. So I write a little c in here, okay? Define similarly for all s, and now you restrict alpha from 0 to n, and you replace the Bessel kernel by the Ritz kernel, and it's just like this. And of course, it turns out that this capacity is the capacity associated to the homogeneous superlap space W dot alpha s that I mentioned earlier, okay? Well, if you work with bounded domain, it's more convenient to work with the Bessel capacity. But if you work with the whole space Rn, then the Ritz capacity will be more convenient. Okay, but locally they are equivalent at least for alpha s less than n, and that's because the Bessel kernel behave like the Ritz kernel when X near the origin, right? Okay, so. Okay, this is also something that's very well known, but I mean, maybe many of you here never hear about this. So, essentially, the situation when alpha s equal to n is the critical situation. In the sense that, say, for the Bessel capacity, okay, for the Bessel capacity, if alpha s is bigger than n, this capacity is just a constant, okay? It's a constant set function, okay? It's a constant set function, so essentially, it doesn't have, okay? It's just, and then for the Ritz capacity, if alpha s is bigger than or equal to n, the capacity of a set is just 0, okay, for any set on a set. So the situation alpha s equal to n is a critical situation, and so in the case when alpha s equal to n, you better use the Bessel capacity, okay? Now, the capacity of a ball is well known, okay? It behaves like the Lebesgue measure of the ball raised to the power 1 minus alpha s over n, okay? At least when alpha s less than n. Now, if you take a general set, you don't expect much, okay? You don't have any good estimate, only some low bound, okay? Only some low bound, and this follow from superlap inequality. You can control by the Lebesgue measure, but of course, you don't have upper bound. Otherwise, you can just use the Lebesgue measure. Why you have to use capacity, right? Okay. Okay. And then again, this condition will tell you that the capacity can be controlled by the so-called Hausdorff content, and the order here n minus alpha s. And of course, I mean, this is well known as well. So now this is the Hausdorff measure. Okay, if the Hausdorff measure of a set is finite, then the capacity is 0. But if yeah, if the house dot content is 0 and the capacity is 0. That's what. Okay. Okay, now let me talk about a little bit about nonlinear, I mean the extremal and nonlinear potentials. So let's for example, you look at the Bessel capacity of a set K. Okay, so as I said, you minimize over the LS norm of F, where the potential of F is bigger than 1 on the set K. It turns out that there is an extremal in this minimization process. Okay, so the extremal function F that realize this infimum is the so-called capacitary function for the set K. It is given by the potential G alpha of a measure mu sub K raised to the power S prime minus 1. S prime is the whole conjugate exponent of S. For the measure mu K here is a non-negative measure supported on the set K. It is called the capacitary measure for K. And the potential of F will be called the nonlinear potential. And my notation is V alpha S of mu. And this is just the potential of the function F. And where F is given by this. So this is the so-called Mazar-Harbin nonlinear potential. Okay? Okay, and if you apply it to the measure mu sub K, then this is called the capacitary potential for K. Now, in the K, when S equal to 2, then S prime is going to be equal to 2, so you get 1 in here, okay? And you yield the summarization of the Bessel kernel, then this having Mazar potential is just the linear potential G2 alpha of mu. Okay, so if S equal to 2, you don't really need nonlinear potential theory. It reduces to the linear potential theory. All right. And of course, the measure here is, it's an extremal measure. So and the F is extremal function. It will satisfy a lot of properties. Okay. Among them, of course, is that the capacity of a set K is exactly the total mass of the extremal measure, and of course, it's also the same as the integral of F to the S. Okay, and because the definition of F to the S is like this, so it's exactly the potential of the measure mu raised to the power S prime. And if you use Fubini, this is exactly the having potential, but you integrate against the measure, okay, not the Lebesgue measure anymore. This is again the extremal measure. So this is Lebesgue measure, but this is not Lebesgue measure. And here you would expect that this, in some sense, the extremal had to satisfy this inequality, right? And it does. It's bigger than 1, but only quasi everywhere on the set K. Okay, and on the support of the measure mu, the potential is bounded by 1. Okay, and because of that, actually you have a new definition of capacity. You can equivalently define capacity in this fashion. You take the so this is like a dual definition. The other one, you take the infimum. Okay, now you can take the overall total mass of the measure mu, where mu is a measure supported on the set K, and the Mazar-Harbin potential is less than 1 on the support mu. It turns out that this supremum here is equivalent to this supremum when you replace this Mazar-Harbin potential by the so-called work potential. Okay, this is something that was introduced by Nguyen yesterday already. So let me mention it again. So I put a 1 here, I mean that the truncated version of the work potential. So you integrate, you want to calculate the work potential of a measure mu at a point X, right? Then you, I don't know if I have enough time, you just look at the the measure at the pole, at any ball center at the point X, and then you divide by the radius to the power m minus alpha, and then you have energy rate to the power s prime minus 1, and you integrate along the t here, along the radius, okay, for any point X in R. And of course, it's easy to see that this potential here is less than the so-called Maser-Halving potential. But in the case when S is bigger than 2 minus alpha over n, then essentially they are equivalent. I mean, they're equivalent pointwise. But of course, there's some, you need to modify a little bit because they truncate here. Okay. But on the energy side, okay, you can think these are the energy. Okay, they are equivalent regardless S. Okay. So for any S bigger than 1, okay, no energy are equivalent, and because of that, you do have this. I mean, of course, I did not give you the detail, but the equivalence here follow because of the so-called Whoops inequality, and this is proved by Whoop in a paper, joint paper between Hedberg and Whoop in '83. Okay, so the energy of the Whoop potential here and the Maser-Halving potential are equivalent. So and because of that, you have this, and that's why at the beginning of my talk, I said that if you know potential estimate for your solution, then you essentially know the capacity, because the capacity can be defined by using Whoop potential like this. All right. So that's the point that I want to make earlier. I want to clarify it now. Okay. It turns out that the Whoop potential plays a very important role in our PDEs, and because in our situation, you can control the solution. I mean, pointwise, two-sided, okay, two-sided and pointwise by the Whoop potential, but not by the Maser-Halving potential. All right. And I want to say that, of course, one should expect that the capacity measure mu sub k for a capacity k is good, okay, in the sense that it's not an L1 function, in some sense. In general, it's not an L1 function, okay? It has to be a measure. In general, it's not an L1 function, but it is strongly continuous with respect to capacity in the following sense. For any set E, okay, say you take any border set E, then the capacity, I mean the measure of that set E is controlled by the capacity of that set E. All right, for any set E. So yeah, it's and the constant M here is independent of the set E. So in other words, this, of course, the point I want to make it that eventually you have to study equation with measure data. The reason is that the extreme mole measure is not a function. It's not an L1 function. But it's not bad. It's strongly continuous with respect to capacity in this sense. Okay? And this is true for any set, not just for ball, okay? It's for set as well. That's important. Okay. If you restrict to ball, you have some sort of monetized space, but it's not good. Okay. It's for set as well. Another thing I want to make is that the nonlinear potential, I mean, it looks horrible, but as I told you, if the G, I mean, if SE2, it's a linear potential, so you should expect that it's not so bad, actually. And actually, it's good in the sense that there exists a delta, say, bigger than 1, in the case S bigger than 2, it's bigger than S minus 1, so that if you raise that thing to the power delta, then it belongs to the class A1 local. Okay, this is in my work with Ken Oil. Okay, of course I should attribute this to Igor Verbitsky. He discovered this in the 80s. He used this in the 80s. I mean, Maser used this in the 80s for his development of Supernet multiplier theory in his book, and he proved this that for the situation of a risk potential, that I mean, if you consider risk potential instead of Bessel potential, then in fact the Maser-Halving potential rate to the power delta is in the class and in the Nguyen-Cong Phuc class A1, not just A1 local. But if you do it with the Bessel potential, you don't expect it to be A1 anymore. It has to be A1 local. And by definition, it means that you look at the local maximal function of that function, and it is controlled by a constant multiple of that function again for any point x. And when I say local maximal function, I mean that it defined like the Hardy-Littlewood maximal function, but you take the sub over R, I mean the radii R, where the radii is restricted to the interval from 0 to 1 only. Okay? So I don't write down here, but you understand it in that sense that the maximal function is defined only, you restrict the radii to the interval from 0 to 1. So you get the local maximal function. And this works because you got the precise decay at infinity for G. The function G alpha decay exactly like e to the power minus the absolute value. This works because of that. If the G decay faster like e to the power minus x squared, for example, it doesn't work, okay? But because it decay exactly e to the power minus x, not x squared, I mean, it's linear, so it works. And moreover, more importantly, that again, you still raise to this power, but if you measure this function in the L1 norm with respect to capacity. By this, I mean that you calculate the level set, and then you calculate the capacity of that level set, and then you integrate along the T here. This L1C norm of this nonlinear potential raised to the power delta here is still controlled by the capacity of the set K. Okay, this is very important observation of Verbitsky in the 80s. Okay, and so what I want to say that even though this function is look bad, but you can think it like it behaves like the constant function, because you see that this is less than 1. So in the minimization process, you should have expected it's like 1, but it's only 1 on the set K in some sense. But outside the set K, you would think it's like 1, but the way to quantify that is that you said that it's A1 local, okay? And if you work with problem in the bodic domain, the locality here is not a problem because, there is a result by Raychardt. If you take away with the A1 local, then you can always extend it. I mean, if you restrict to a ball or a bodic set, then you can always extend that local A1 function into a local A1 weight. Okay, so no problem. And now, so do we have time? Okay. And now I talk about capacity strong time inequality. It follows from the definition, just a definition of capacity, that you have this width type inequality, like the capacity of a level set is controlled by this quantity. But then in the 60 and in the 70, there are some very important results about the so-called capacitary strong type inequality. And originally it was due to Mazur, and then it was later on improved by Adam, Jarberg, Hansen, etc., etc. It said that if you look at the potential of a function f in Ls, then you calculate the Ls norm with respect to capacity, meaning you calculate this integral, I mean one-dimensional integral. This is controlled by f to the s. So this is strong type. But if you look at this is strong type and this is weak type. Now, recently we were able to prove this. If you take L1 norm instead of Ls norm, then the right hand side becomes f to the s, and then there's a way here exactly g alpha f to the power 1 minus f. Adam in 98, he proved this inequality for a rate potential only with the integer alpha. And then he have a conjecture that this should be true for non-integer alpha, and we settle this in our paper here. In fact, his proof doesn't work even for the Bessel potential, and even for the integer alpha, because he used singular integral in his approach. And there's some problem when you do that, when you deal with the Bessel potential. So because of the decay at infinity. So we give a proof that it works for non-integer alpha, it works for real potential, and also work for the Bessel potential. But I mean, this paper is not available yet. We are still, writing it, finishing it. Okay. I mean, this is related to other works as well, like Nigel Carlton and Verbitsky, and then there's the work of Barras and Pierre and so on. I don't mention explicitly here, okay? But I want to say that there is other strong tie, capacity strong tie inequality that's available, okay? And then from that capacity strong tie inequality, we have the following very important characterization of phase inequality. Now, if you look at this inequality for OF, okay, you want this, so mu is a measure, okay, mu is a measure. You want this inequality to hold for any measure mu, for any function f, then the necessary and sufficient condition is that your measure is exactly behave like the extremo measure that I mentioned earlier. For any set, it is strongly continuous with respect to the capacity, okay, so that makes the point, like why that important. And again, this condition is essentially equivalent to this condition that it's just a weighted Poincare overlapping inequality. Important, I want to make a remark that the S on both sides are the same, okay? The S on both sides are the same power, but there's a weight in here. And then you want to find a weight, mu here, so that you have this for all phi, and the condition is this capacity condition. And this has to hold for all compact set. You cannot restrict to both, okay? Okay, and there are more equivalents, due to the work of Mazur, Verbitsky, and also more. I mean, I did not mention it here. There are also conditions due to Verbitsky and so on, and there are also the so-called Kerman-Sawyer condition. So this capacity condition is equivalent to this and equivalent to this. This is what we call the Sawyer-Kerman, the testing condition. Basically, what you do is that you realize the inequality and then you test with a characteristic function and you get this. And this is for balls. Okay, this condition is a ball condition. You just check it over ball. This condition is not a ball condition. It's a capacity. It's a compact set condition. You have to check over compact set. Now, just imagine that if you have this only for balls, then you only have this for weak. I mean, the Lorentz, the weak LS infinity, S prime infinity of this one. But because this is true for all compact sets, so you have this for strong LS prime norm here. Okay, so there is a very important subtle difference between Morey space based on L1 and then the capacitory space. I mean, based on capacity here. Okay, so you do have strong LS prime here, not weak LS prime. Okay. So now, well, I think I can wrap it up now. So I want to make, so the point of my talk is that, so we do have potential, eventually we do have potential estimate for our equation. And of course, this is the fundamental result due to Cuban, Leinert, and Mali. So for a Biller-Potts equation, you have, for non-analytic solution to the Biller-Potts equation, you have two satisfied by the work potential. This is W1P, okay? So this is n minus p, this is 1 over p minus 1. And if you work with, if you work in the whole space Rn, and if the infimum of u is 0, this is a very mild assumption, then you have two satisfied like this. So if I don't write anything here, I mean R equal to infinity, okay? And of course, the Kb equal to 2 go back to the classical Newtonian potential, okay? Because as I told you earlier. Now for the K Hessian equation, it turns out that you have to use the work potential alpha s, and the order of derivative here is like 2k over k plus 1, and the s here is k plus 1. Okay, and because of that, the capacity associated to this Hessian operator is exactly that, the capacity with those orders. Okay, and the fundamental result of Laboutine is that you can draw the solution by two-sidedly. This lower bound is also important, okay, by the potential and so on. And now I will not go into details here, but now you can use the thing that I mentioned earlier, capacity, strong time inequality, warp inequality, and so on. Then you can solve. You can look at this equation with a measure, and then you can solve this. And then this is you can find a sharp condition on mu so that you can solve this. if mu, if there is a solution, then the measure mu has to be good in the sense that is controlled by the capacity here. But there is some interaction here. It becomes, the interaction between the P Laplacian and the U to Q gives you the so-called, it's a fractional capacity. Okay, if you remember the work of Adam and Pierre, it's a two capacity of order 2 and then Q prime, but now it's P, and P may not be an integer anymore. So it's a fractional capacity, okay? And the order here, the degree of integrability here, Q over Q minus P plus 1. So this is exactly the conjugate exponent of Q over P minus 1, okay? So if there is a solution, then the measure is regular, and conversely, that there is a constant C0, so that if the C is less than that C0 and mu satisfy this, then you have this, then you have a solution to this. So, what I write here is not very precise. There is a gap in the smallest constant here. Necessary with one constant and sufficiency with another constant. Okay, so there is a gap in the constant here. And I work with renormalized solution and so on, so I don't restrict any condition on the domain, on the boundary of the domain. And earlier work on this include the work Renon, where she considered the subcritical case. The subcritical case is the case where this product is equal to n, okay, or bigger than or equal to n, okay. When you know the capacity, you would know what is the critical situation. The situation is when the product of P and this one is bigger than or equal to n. That I explained it to you about the capacity earlier. Because in that case, the capacity is just a constant for any point. And then, in particular, this actually solved a conjecture by Bidault, if we're wrong, in around 2000. And earlier work on this in the linear case include Paras, Pierre, Adam, Pierre, and Carlton, Verbitsky, and Witten, etc., etc. I did not say it explicitly here. And because of that existence, you can see that the removable set for this equation is exactly the set with 0 capacity, and now you yield this capacity, okay? So it's no longer the big capacity anymore, but it's another fractional, it's associated to some fractional superlapse space. Okay, so maybe let me mention to you that how do you prove the necessity parts here? Okay, how do you prove that the necessity part? The idea is that so you assume that any solution, on a set here can be extended. Then you say that if the set E is not, if the set E is of positive capacity, then you can find a solution so that it cannot be removed. Okay, the set E cannot be removed, and how do you find that solution? Well, you solve it, right? So by contradiction, suppose that the capacity is strictly positive, then you look at the measure mu sub E, which is the capacitary measure for the set E, and then you know that the measure mu E satisfies that capacitary condition. Then you can always find a solution to this problem because of that existent result for some small epsilon, okay? And because this is it's a non-zero measure and it's supported on a set K, so you can never remove this one, okay? So that's the idea. And then you have a similar result for the K-Hessian equation, but in this case you have to use a different capacity. And it turns out that the interaction here will give you different capacity, and the capacity is of order 2K, and the degree of integrability is Q over Q minus K. All right, and the removable set is the set of 0 capacity, and the capacity is the same capacity here. Okay, so tomorrow I will talk about equation with the radiant term. So for now, thank you very much for your attention.